Welcome to the world of nuclear power, where the world is powered by nuclear power. But what is nuclear power?
There are two types of
Okay,
nuclear...
dude, cut it out. This isn't some 50s science film.
I'm sorry.
Okay.
I'm sorry. Sorry. All right, there are two types of nuclear power, fission and fusion. When most people think of nuclear power, they're thinking of fission. Fission occurs when a large, unstable nucleus splits into two smaller, more stable atoms.
So what is fusion?
Well, fusion occurs when two relatively unstable atoms combine under the right conditions into a larger, more stable atom. For example, two isotopes of hydrogen, deuterium and tritium, combine. They create a helium-4 and release energy. This energy was initially used to hold the atoms together, and it's released as a neutron and radiant heat.
So why haven't I heard of any fusion reactors?
Well, there is one. The sun releases enough energy in 10 seconds to boil the Earth's oceans, and it maintains a constant core temperature of 150 million degrees Celsius.
That's great, but how do we contain so much raw power?
Raw power! Yeah. Anyway, scientists have been working on this problem for years. Initially, nuclear fusion was used as a weapon. Starting in the 50s, the US, the USSR, and the UK were all working independently on the problem of harnessing nuclear fusion for more peaceful uses. It wasn't until 1985, at the Second Geneva Conference on the Peaceful Uses of Atomic Energy, that these countries started working together. This led to the development of the Joint European Torus in '91, which was the first magnetic confinement reactor to achieve controlled release of fusion power. The big news now is ITER.
Oh, I've heard of these guys. They're the ones in France, right? Aren't they building something called the Big Mac?
Actually, it's called the tokamak. But I could see how you get the two confused. I mean, one's a fusion reactor, there's a hamburger. You're pretty close.
Anyway, you still didn't answer my question. How do you contain such raw power? Are there any materials that can withstand such high temperatures? Besides, what's the point of developing a fusion reactor if we already have fission reactors?
First of all, fusion reactors are cleaner and require less fuel. Fusion reactors are also much safer. Since fusion can only happen in a specific environment, if anything goes wrong, the reactor shuts itself off. Fusion fuel is also much easier to obtain than fissionable material, and the waste products, while more radioactive, only stay that way for around 300 years, as opposed to tens of thousands.
Wait, didn't you say that the fuel materials were relatively easy to find? I thought tritium was really rare.
Yeah, it is, but scientists think they have a way around that problem. Once they achieve sustainable fusion, they're going to start experiments on tritium breeding in the walls of the reactor.
Breeding?
I've been really trying, baby.
Not that kind of breeding. This is done by lining the walls with lithium. And then when the high energy neutron from the fusion reaction hits the lithium, it splits it into a tritium and a helium.
Man, that really is better. So this tokamak reactor is the next step in developing nuclear fusion reactors. Is this one of those magnetic confinement reactors you were talking about?
You know what? I'm sick of this. Let's try something completely different.
And now for something completely different. A man with 3 buttocks.
Go.
As I said before, selecting materials for fusion reactors is tricky. Temperatures inside the reactor can reach upwards of 150 million C, which no material can withstand. For this reason, there are several parts to containing the fusion reaction. The first defense against such high temperatures is a magnetic confinement field. This prevents physical contact between the plasma and the reactor wall.
So this way you aren't using an actual material to contain such high temperatures.
Exactly.
But how do you stop the neutrons and radiant heat?
Well, for that, we have the inner wall or blanket. The purpose of the blanket is to slow down neutrons and dissipate heat. It is a modular blanket made up of 440 individual segments of beryllium. Beryllium has been selected for several reasons. First of all, beryllium has a high thermal conductivity and specific heat, which allows it to act as a heat sink. The heat is transferred into coolants, which are used to create electricity. Beryllium also has a large, high-energy neutron scattering cross-section, which slows down neutrons into the thermal range. A thermal neutron is one whose energy corresponds to room temperature.
So the beryllium basically just gets in the way of the neutrons.
John, wake up!
Sorry, what were we talking about? Oh yeah, the beryllium blanket. So is that the outer wall of the reactor?
No, the blanket is supported by a vacuum vessel. The vessel is made of double steel walls with space for coolant to flow around. Surrounding the vacuum vessel are magnets, which create the containment field.
Magnets like this?
Not quite. These magnets are made up of superconducting niobium tin and niobium titanium alloys, cooled by supercritical helium to negative 269 C.
So what you're saying is containment isn't just a materials issue, but a combination of material science and physics.
Indeed. The sun creates enough energy to boil the Earth's oceans in 10 seconds. And it maintains a constant core temperature. Don't smile at me. Well, there are two types of nuclear power, fission and fusion. The most, when crap. All right, go from right there. When most people think of nuclear power, they're thinking of fission. I don't know that line. Exactly.
Temperatures? Sorry.
God dang it. Exactly. All right, say it.
Temperatures?
Exactly.
Heat. Radiant heat?
Fuel. They're also safer. Fusion reactors only need a specific environment to happen.